All right, so this video is going to be a little bit different from the other ones. I basically have been kind of curious about this, and I think I figured something out last night. So I've got a funny book here. It's the Signals and Systems Demystified, because gotta read the easy books to learn the hard stuff. So I noticed. I guess I'll take one step back. I think polynomials are really powerful, right? So the function space is dense in the polynomials, or maybe I say that backwards, but in any case, you know how like the real numbers can be approximated as well as you want using the rational numbers? Well, the same thing happens with polynomials, right? Basically, any function, you can approximate it as well as you want by adding up polynomials. So in my head, that means polynomials are pretty powerful, right? You can approximate any function with a polynomial, and Taylor series or power series are a way to do that. And a Taylor series is basically just a prescription, a way to compute the coefficients, right? So I'm gonna hide this book and I'll bring it right back in 1 second. But so basically, you have some function. Oh, where's my pen? Okay. So, f of x, and then you want to say that's approximately equal to, a1 times x to the first plus a2 x to the second plus a3 x to the third. And what, so it's, everyone knows, not everyone knows, but I mean, like, it's known that, what you're trying to get it in terms of is, x to the 0, so a0. Can't forget that constant term. That your x's are ascending like this, and so really your goal is to just compute these coefficients, right? And that's how what Taylor's theorem says is just, it gives you a way to compute these by calculating the derivative of this function, right? And so that's a cool way to do it. That's fine. I was thinking, maybe there's another way to compute these coefficients, because basically what I'm saying is there's a lot of power in being able to approximate some function by, these x's ascending, right? Because all these functions are dense in these polynomials, right? So if you can get the right coefficients, you can essentially approximate any function. So that's kind of the power. And I was thinking, maybe you could do this a different way other than using Taylor's series and using the derivative and stuff. So what I did find was I found the Z transform, and that's where this comes in. I don't know if this thing is focused. Okay, I guess it is. So this looks a lot to me like a power series, right? Because you've got some function that's Z, so that's the complex variables, is equal to the sum from negative infinity to infinity. So it's a little bit different because it goes in both directions. It goes negative infinity also to positive infinity, whereas what we're used to is just going to positive infinity. But in any case, now you have some discrete time signal, so xn. So this is just at discrete values, you're getting a number, and times z to that integer power, right? And that's exactly what this is, right? You have some real value, or not real, it's actually going to be complex, but you've got some number times, z or x to just an ascending power. So I was like, oh my gosh, this is what we're looking for. And so the Z transform goes from those power series coefficients to some function of Z. So I was like, oh, well, we want the inverse, right? We want to go from this to get these power series coefficients. And so, and actually this book, it has, I love this book, but so the inverse Z transform, it doesn't really tell exactly how to do it. So I wish it did, and I would have just shown you, but I found it on Wikipedia because Wikipedia is awesome. And then I wrote it here. So here's that Z transform, right? So you've got this signal, discrete signal, and then you do this, and then you get your coefficient, or you get your complex function. But so the inverse is, here's your complex function, and then you're computing these coefficients. So this is a way, just like Taylor series, to compute these coefficients on the power series. So I was like, this is amazing. Like, I was wondering if this works. And so I'm going to overwhelm you here with my notes. So I apologize. But so here's what I'll do, what I was trying to do. I was trying to see if it worked, right? So what I basically said was, in this case, x of z is the function you're trying to approximate, right? By using these coefficients on the power series. And so that's what I was trying to do. So I used a function I knew, right? If my function was z to the first, I knew what my coefficients would be. It would just be, x of n is going to be 1 and all of the others are going to be 0, right? And so it actually worked. Like, you can see here, I plugged in z for x of z, right? So this is essentially where we were, right? And one thing I do want to give a heads up on is these go opposite of each other. Like, you can see as n increases here, it's going the opposite direction here. So as xn goes up, z goes to the negative n, so 1 over z or whatever. So and in a power series, in typical what you're used to, these are all positive numbers. So actually, what the funny thing is, what we're computing are going to be these negative ones. So you can see here, I wrote x sub negative 1 because I wanted to see what the power series coefficient on z to the first would be. So my goal was, I was hoping that this integration gave us 1, and it did. So I plugged in z here, right? And then I plugged in negative 1 for that n. So z times z to the negative second, right, is just z to the negative first, right? And then this integral, I actually saw it sort of in a table, but that integral is 1. So what we have is 1 times z to the first, which is exactly what we have. But now we just need to say, well, are all of those other n's 0? Because, we have this right, but if it was like adding on plus, like plus 2 times z to the second, then it would be wrong, right? It wouldn't work. So I was hoping that for these other coefficients, it would give us 0. And that's what we're proving here. And that actually did work because, x is 0, you've got this, you're plugging in 1. No, you're not plugging in 1. You have, where is it? Right here. So this one is z, right? And then z to the negative, z to the n minus 1. If n is 0, right, you have z times z to the negative first. That's why you got 1 here. And so this is a integral along a closed contour of an analytic function, so that's 0, right? So x is 0 is 0, which is exactly what we wanted. And then I wanted to prove that for the rest of these, it was also 0. And so when you plug in 1, you get the integral of z along that closed contour. Z is also analytic, so you're going to get 0. And x to the negative 2, right? Now you end up here, and I was like, oh, this one. So basically I realized that, going upward, you're always going to get some analytic function here, so you're always going to get 0. And then I was wondering, what if you plug in negative 2? If you go the other direction, do you also get 0? And so I was like, well, maybe not, because now we don't have an analytic function. So I was like, well, how do you evaluate that integral? And basically how you evaluate the integral is by using, some complex integration methods. And if you do all the work, you end up getting e to the negative 2 pi I minus 1 times this stuff. But e to the negative 2 pi I is 1. So that's 0. So this is 0. So what that proves is, we used the inverse z transform to compute the coefficients on a power series to approximate some function. And that's crazy because, you're used to using Taylor series and computing the derivatives, but we did it with a complex integral. So it's kind of cool, and I don't exactly know where it'll be useful, but I feel like it will be. And that's just a little bit more proof and stuff. And then so this one, I think this is kind of just isolates it and distills it down. So basically, x to z, I'm basically just pulling, I think you can see it here. So what we're saying is x to the z, or x of z, right, is equal to, and now this summation is what we've kind of expanded partially out. It goes on forever in both directions. But we pulled out this 1 over 2 pi I, right? Basically what we did was, xn, so we've got this function here, so we just plugged that in right there. That's what we're doing here. So we've got a contour, so this z to the negative first, well actually this is times 1, right? So this is basically how you're computing the coefficients in the power series. So this is essentially 1, right, times 1. And now this is times z to the second, times z to the third. And remember how we said it goes both ways. So I kind of, drew it like this, right? So this is it going one way, and then this is it going the other way. So z goes, z climbs, right? So we have first, or we have zeroth, this is 0 to the 0. We have z to the first, z to the second, and then here going this way, we have z decrementing. So this is z to the negative first, z to the negative second. So as you can see, that's basically how a power series is set up. So all of these little things, right here, I can use my highlighter. So this, I should do it a little better. So it's that, and then that part, I'm hooking this off because what I'm trying to show you is these are the coefficients. So this is basically the formula to get the coefficients of the power series. So instead of using a derivative, you can use this complex integral. And, depending on the problem, this actually might be easier. I don't know. So yeah, that's kind of the beauty. And then, just to really hammer the point home, when our x of z we were trying to approximate was just z, this turned out to be 0. This turned out to be 0. This turned out to be 0. This was 1. And this was 0, and all along these were going to be 0. So it worked on this example. So we just kind of need to test it on others or prove it or kind of do any of that stuff. But